Welcome back to ECE 220. If you're reading the title, I'm hoping this will be useful. Some of you may have already finished pre-lab number 5. I'm not sure. I'm guessing some of you still haven't yet completed it. If you haven't, I hope this will be helpful. That's what we're going to focus on today. But all of Chapter 9 is dealing with complex numbers, so you need to be thinking about or reviewing that topic, and Appendix B is dedicated to complex numbers. Hopefully you find that helpful if you need review on complex numbers. Group A, your lab number 4 report is due today. That's Wednesday, and no class, so our last class period of the week is tomorrow. I'm not going to get oriented this entire week, but today is Wednesday. We have a class tomorrow, no class Friday. But if you are in Group A, you will need to complete your pre-lab by Saturday, and Lab 5 starts next week, and I'm trying to now help you today with the machinery, the tools to compute what you need for the pre-lab for Lab 5. We'll sort of back up and start Chapter 9 fresh, but today I want to sort of give you the necessary steps with which to complete pre-lab number 5, and that's going to actually, lab number 5 involves Chapter 8 and Chapter 9 material. So we'll first look at, and I didn't say, but homework number 12 is due next week, and I think we'll have about 15 total homeworks, not 15 more homeworks, but we're having one every week, and so in keeping with that strategy, homework 12 is due next Tuesday. Today we'll start with Chapter 8, which is first order circuit behavior. What do we expect to have happen? And then we'll get into Chapter 9, which requires us to look at, after the transient, when we're in steady state, what now happens in sinusoidal steady state analysis. And we'll need then to figure out, what does a resistor look like as it experiences different frequencies? What does a capacitor look like? In Chapter 9, we'll obviously look at what inductors look like in terms of what kind of impedance, or I would say, if impedance seems a little odd, just think of frequency-dependent resistance. The resistance now varies as a function of frequency, and that's what we call impedance. And then we'll look at analyzing this same circuit with different parameter values, or with different elements in the lab, different R's and different C's, what that looks like when we excite it with a sinusoid. And in fact, this particular circuit is a low-pass filter, and that just means that it passes low frequencies and it reduces the amplitude, or it tries to attenuate higher frequencies. And what constitutes low frequencies obviously depends on the circuit, or the values, the specific values of R and C. For pre-lab Part 1 in lab number 5, this is trying to get you comfortable with pre-lab for lab 5. This is now Chapter 8 material. This is a first order circuit, and they now want you to determine what's going to happen in this circuit when you actually apply a square wave input at V sub I of t. And they give you then the parameter values. You have a 1K resistor, and you have a 1 microfarad capacitor what is the voltage across that capacitor going to look like when you present that circuit with this particular input. And the units on the horizontal and the time axis are in milliseconds. We now have this square wave starting at 0. It goes for 10, and I don't even know what the amplitude is. Does somebody remember the amplitude? It doesn't matter. I don't remember. I forgot. I should have looked that up. But let's just call it A. So we have an amplitude A, and now we want to know, what does the capacitor voltage look like relative to the input waveform. And here, with an RC circuit, you can sort of think of this capacitor charging up as it's presented with a constant input. It's presented with many different constant inputs. First it has amplitude A, then it gets set to 0. Then it sets to A again. Then it sets to 0. What's happening as you cycle back and forth? And my question is, where is infinity? How fast does this circuit respond to this particular constant, or these constants as far as inputs are presented to it? Is it slow enough that it hardly even gets off the floor when it's excited with a constant of A? Or is it fairly quick? Does it get to A fast? Or is it somewhere in between? So we can figure that out by determining what's infinity. And when I say what's infinity, this is what we're essentially saying we're living in chapter 9, is we're beyond infinity. We're now into the steady state behavior. The transient has disappeared. In this part, we're worried about the transient. How long does it last? And what is the rule of thumb that we are using to describe the transient interval? It's so many tau. That should give it away, right? How many tau do we have to wait before we are considered finished with our transient behavior? And that's 5. So we have 5 tau. That's infinity. And can we figure out what tau is for this particular circuit? What is tau in a first order RC circuit? That's the time constant. That's what tau is. Tau is R times C. If we can now find tau, which we can since we are given specific values of resistor and capacitor. This was 1,000. The capacitor was 1 micro. Or we now have tau being 1 millisecond. And if we have to wait 5 of those to reach infinity, we now have 5 milliseconds for our transient to be finished or completed. And does that help us now sketch this? What was it called? V sub O or V sub C? Here I think I called it V sub C. I don't know if that's what they call it in the pre-lab or not. Can we now sketch this? What's an RC curve look like, or shape look like? The transient. Isn't that just this exponential shape? And it's finished by 5 tau. So now we say, oh, we're just halfway between each of those 10 millisecond intervals. We say, oh, by 5 milliseconds, we're now finished. Oh, now we have to see a new input, see another new input, and we have some shape like that has this RC behavior, this RC time constant shape to it, and depending on the values of R and C, you either get to A quick or not so quick. So if you had a slower infinity, then you might not get up to A before you now transition to 0. Or if you had a very fast system, then it would quickly zip up to A, and that exponential shape would then look almost like the square wave input if your time constant was really fast. That's part 1 of pre-lab. Now, in the second part, we go into chapter 10. Chapter 9. Chapter 10 is power. Chapter 9 is sinusoidal steady state. And we now are assuming the transient has disappeared. We hit this with a cosine. Initially, there's going to be some transient behavior. And after 5 tau, where tau is RC, again, this is an RC filter or an RC circuit, but now the parameters for R and C have been modified. And they want you now to analyze this circuit for 3 different frequencies. And these frequencies are spaced quite far apart in terms of frequency distance. One is at 10 hertz. One is at 1,000 hertz, and another is at 100,000 hertz. And if this is a low-pass filter, if we are passing low frequencies, you can expect that these 3 frequencies have been selected judiciously to give you a feel for how this input gets attenuated as the frequency gets higher. You would expect that at 10 hertz, maybe V sub O might look very much like V sub I. At 1,000 hertz, well, then maybe that has something to do with the bandwidth of the low-pass filter. Maybe you're at about the half power frequency, which we haven't talked about. You don't really need to know, but you do want to be thinking about what this looks like behavior-wise, and I don't even know if I want to draw this, but in 320 you'll start talking about frequency response and Bode plots. And that means that you're interested in what's the magnitude of this filter, and that filter will be described by a transfer function. And it might be passing low frequencies and then it starts to roll off. Here is the cutoff frequency of that filter. This axis is usually in logarithms, but now you can hopefully see that the magnitude, and there's also a phase plot. How does the phase change? So we are going to be seeing that in our answer. We'll see a amplitude modified and a phase shifted cosine at the output. But we want to know if we're shaking this circuit at a particular frequency determined by F, what is V sub 0 of t? Well, we know, since this is a linear system, that the output is going to be moving at the same frequency. It's going to be shaking at exactly the same frequency. We just want to know what's the magnitude and where is it experiencing peaks relative to the peaks of the input waveform or sinusoid. And here, realize that a lot of our analysis that we play with involves omega. In the lab, you'll be adjusting the knobs relative to F. So in hertz, that's F. In omega, that's radians per second. The relationship is 2 pi F is equal to omega, where this is now cosine of omega t, or cosine of 2 pi ft. We want to now determine the output voltage, and let's now go back to our buddy Euler. Let's do a brief review of phasors. Euler gives us this beautiful formula, or beautiful relationship. It now relates sines and cosines to a complex exponential. Okay, beauty is in the eye of the beholder. I will give you that. But you'll start to appreciate this expression. E to the jx is cosine x plus j sine x. If we wanted to just look at the real piece, or the cosine, we could just take the real part, and we'll typically abbreviate that RE of the argument being this complex exponential. Here I'm just saying the exponential is jx, but in our analysis we'll actually make it a function of time. In the bottom line, you can see then that cosine of 2 pi ft, which, remember, this is now our omega, that's cosine omega t. We'll just be thinking of this as the real part of e to the j omega t. And what can you, if e to the j omega t gives you heartburn, that's fine. No, it isn't. We'll take some Tums, or we'll take some antacid or something, and what we'll take is understanding what that is. That's just a phasor that's rotating counterclockwise about the origin. And what's the magnitude of e to the jx? If I had to compute the magnitude, if somebody said, oh, what's the magnitude of e to the jx? That's the magnitude of a complex number, which is now the square root of the real part squared plus the imaginary part squared. Remember, when we play with complex numbers, real numbers weren't giving us enough information. We needed to now go two-dimensional. So now we go horizontal for the real part and vertical for the imaginary part. We now have this plane, and any point on that plane is a number. It's a complex number. Just like when you walk along the real axis, you get to some spot, you're at some number. Well, now you can walk on a plane. We needed more flexibility, or much more capability. When we were dealing with polynomials, we needed to expand our number field. We wanted it to now be complex. So now I'm asking, if we were at a point in space, e to the jx, how far away are we from the origin? Well, now we would go horizontally, cosine of x, and now we're saying, oh, we're just looking at the hypotenuse. So let's now take the cosine squared of x, the real part squared. We take the imaginary component and square that. And now you remember your trig. Cosine squared plus sine squared . If you see e to the jx, that's just a distance of 1 from the origin. And the jx gives you the angle. The x is the angle that complex number makes with respect to the horizontal real axis. If I now said, what's the angle of e to the jx, that's now just x. And you could see that if you simply said, oh, here is e to the jx, but now this is cosine of x, and this is sine of x, that distance. And now that particular angle is x. And how far that point is away, if we just have e to the jx, we're a distance of 1 from the origin. Obviously, if we scaled that, if we said, oh, it's 5 e to the jx, now we're 5 away from the origin. And if it's e to the j omega t, we're spinning around with a frequency of omega. And every 2 pi units, we're back to where we began. All of that to help us get into the frequency domain to do phasor analysis. We want to now, instead of having to deal with sines and cosines, which get messy when you're adding, subtracting, dividing, multiplying, let's now play with complex numbers. Then it's cleaner, and we can go back and forth. Oh, you give me a time domain expression, I want to go into the phasor form of that, or into the frequency domain. I want to play or do my analysis in the frequency domain, and at the end I'll give you back your time domain answer when I get the analysis complete. What we do is we do this phasor transform. If somebody now gives you a number or an expression, a cosine omega t plus theta, then the phasor transform of that is like taking the real part of this complex exponential, but the phasor transform likes to see that complex exponential, because really, here's where we're at the restaurant again. We have the omega on the side. You're ordering your food, which is this cosine waveform. It has an amplitude A, it has a frequency omega, and it has an angle theta. What's important? You know, if you're exciting that circuit at a frequency omega, everything in that circuit, once you get steady state, is oscillating at omega. You can put that on the side. You know that's true. That's why I'm saying put it on the side. What's important is the amplitude and the angle. If you know the amplitude and the angle, you can go back into the time domain. You know everything's shaking at omega. It's now the amplitude A cosine omega t plus that angle. And that's what the phasor transform does. It simply extracts the amplitude and angle from this time domain waveform. A cosine omega t plus theta. We say, oh, omega, let's keep note of that. If it's 10, if it's 100, whatever, we know what that is, and that's spinning us around. But if we now took a snapshot, we would figure out, oh, what's the amplitude and what's the angle when we took that picture. That's what's important. We know it's still spinning at omega, but we need the amplitude and angle, and that's the phasor transform. Let's see if we can do some examples. Oh, and we're assuming that when we do the phasor transform, we are focusing or using cosines. We have cosines and sines, and if they're at the same frequency, they basically give us the same information. One is just offset from the other. Let's just agree that when we take the phasor transform, we're starting with a cosine, so that we're all using the same time zero point. If that's the case, I want you to now apply the phasor transform to some examples. If I say, oh, take the phasor transform of a cosine 6t plus 15 degrees, and the other thing that you have to just get used to is the fact that the angle theta, sometimes it's expressed in degrees, sometimes it's expressed in radians. If you're plugging all of this into a calculator, you need to make sure that you have the argument. This 6t, what is it? What are the units on it? 6 is the omega, that's radians per second. time is in seconds. So that first term is in radians. But it's just convention to let that offset be an angle in degrees, or sometimes it's in radians. You just have to know, and if your calculator is set up to always be using degrees, then you need to make sure that the argument, two terms in that argument, are compatible. They're both in degrees before you add them. Otherwise, you'll get the wrong answer. All of that said, what's the phasor transform? Or now let's go into the frequency domain. What do I write down on the right-hand side? What are we extracting and what are we sort of keeping on the side? All right, quit playing with me. Give me an answer. I need a magnitude and an angle, correct? We okay with that? That's the phasor representation of that time domain waveform. What about this one? This one we would say, oh, everything in the circuit is oscillating at 5 radians per second. What's important is that I now have 10 at pi over 4, or 10 at 45 degrees. Pi over 4 was in radians. One more. What's this one? What's the amplitude? What's the angle? It's not quite right because now we have this sign. And to go from the into the phasor domain, we need to make sure that all of our time domain waveforms are starting in the cosine form. So we need to now convert these sines to cosines, and we can keep in mind our trig identity of the sum of two angles. Cosine of A plus B is cosine A cosine B minus sine A sine B. Here, if we want the cosine omega t minus 90, now we're focusing on that combination of sines. We can now say, oh, this is cosine omega t cosine of 90 plus sine omega t sine of 90. What's the cosine of 90 degrees? That one's 0. Sine of 90 is 1. So now we see the connection between cosine and sine. I give you a sine. You say, oh, I'm going to convert that to a cosine. You just take 90 degrees from the argument. So if that's the case up here, then this would be 5 cosine 10t plus 30 degrees minus 90 degrees, so that now this is 5 at minus 60 degrees. When you see sine, you want to convert it into a cosine. And now we know how that's done. And the sine waveform then lags behind the cosine waveform by 90 degrees. That's another way you're going to hear leading and lagging. Here, the sine lags behind the cosine. It's a cosine minus 90 degrees. Let's now use some of this information to see the frequency dependence of our resistors and capacitors, because we need to know that in order to analyze this RC circuit in the sinusoidal steady state. So we're representing sinusoids with complex exponentials. What's Ohm's law? V is equal to Ri. V and I are instantaneous. You give me an I instantly give you a V. I just need to know the proportionality constant, which is the resistor R. There's no memory, there's no derivatives or integrals in that current voltage relationship of the resistor given by Ohm's law. V is equal to Ri. Thus, if we start with the complex phasor representation of the current in that resistor, we'll just take the real part to get the cosine of omega t. Let's now carry that through and use that when we want to now compute the voltage dropped across that resistor. I apologize, we have a couple of R's going around, but hopefully you can keep track of one being the resistance and one being the function Re for taking the real part. We want to now put everything inside the arguments of the real function. We can push that R through or inside. We now have Re to the J omega t. We can now look at this. This whole thing is now the complex exponential form of our voltage. And we know that e to the j omega t was actually the complex exponential of our current. What scales that current is then the impedance. And that was due to the resistor, so we'll call that Z sub R of omega. And R does not have any kind of frequency dependence at all. So this is supposed to verify or convince you that if we go into the phasor domain or the frequency domain and the sinusoidal steady state, our resistors just come in unaltered. We don't have to worry about frequency. They look the same no matter what frequency we're using in the circuit. Z sub R of omega is R. Contrast that with a capacitor. We have ice. I sub C of t is now equal to C dV sub C dt. And now what we want to do is we now want to define our capacitor voltage in terms of a complex exponential. Now we do have memory. We do have this differential relationship between current and voltage of a capacitor. If we now look at I sub C of t, that's now C times the real part of e to the j omega t, but now we need to actually differentiate that. And luckily that real function we can slide constants, we can slide the operation of differentiation into the argument of that real function, and so now we have c times real derivative of e to the j omega t. Let's go ahead and put the capacitor value inside there, and now we have c. What happens when we differentiate e to the j omega t with respect to t? Just get the piece of the exponent that's scaling t, or we now have j omega e to the j omega t. Or if we rewrite that, we now have j omega c times e to the j omega t. And that's now the complex exponential form of our current. And if we wanted to make that look like an impedance, because this is now our voltage, what scales the voltage is now, or if we divide the voltage by an impedance, we'll get a current. So now let's represent j omega c by 1 over j omega c. Gives us the same thing. Or we now say we have 1 over j omega c times e to the j omega t. That's the complex exponential form of our current. This, not all of that. What we're dividing the voltage by is our impedance, just like I is equal to V over R. Now I sub C is V over Z sub C. This is now the impedance expression associated with our capacitor. This is our voltage, and that entire inside the curly braces is our current as a complex exponential. And hopefully this now convinces you that this impedance, due to the capacitor, does depend on frequency. You change the frequency f, or omega, to pi f, you're going to change the impedance, and it's actually complex. We have a j in there. It's not just a magnitude. It's a magnitude at an angle. So now let's use that information to help us analyze this low-pass filter circuit using phasors. We're going to apply to this circuit a voltage, a cosine waveform, 2 pi ft. What's the phasor form of that? And here I'm trying to now indicate the phasor by the overbar. What's the magnitude of capital V sub I bar? It's hidden, but it's 1. And what's the angle? Again, it's hidden. It's 0 degrees. That's our input. So we now know that the input is there. It's a complex number, 1 at an angle of 0. We have the impedance of our resistor, which is 16,000 ohms. We have the impedance of our capacitor, which C is given to us as 10 nanofarads, or that's now 10 times 10 to the minus 9 farads. That's C, and that's not changing. The only thing we're changing is what's on the side, what you will adjust the knobs to, and the lab, which is the F, the frequency. That'll be 10, 1,000, and 100,000. And that's obviously going to change Z sub C. Let's look at the first case. The first case is when F is 10 hertz. And what you can do, we have this augmented reality capability in this class. We put those goggles on, and what do we see for that capacitor? Now we sort of see a morphed resistor. It presents some complex impedance, but if that was just a resistor, do you see how you would find V sub 0? Go back to chapter 3, whatever it was, when we were doing just resistive circuits. We have two resistors in series presented or excited by a constant. What would you say the output across that second resistor was? Voltage divider. We can do that now in the sinusoidal steady state. We have an impedance, Z sub C, and we have a total impedance, Z sub R plus Z sub C. The voltage divider now, to give us V sub 0 bar, this phasor output or number, is just going to be a voltage divider, Z sub C over Z sub R plus Z sub C times the input, V sub I. That's what we want to do here. We know what omega is. That's determined by our frequency F, which is 10 hertz. This is now Z sub C over and what is, can I do Z sub C by itself? Z sub C is 1 over j omega C. And we know what omega is. That was 20 pi. That was 10 hertz, so 2 pi F, 20 pi, and C if I multiply that by 1, j over j, I get j squared in the denominator. That gives me a minus 1, and I now have minus j times 1 divided by 20 pi and 10 times 10 to the minus 9. That ends up being, did I do it? 1.592 times 10 to the 6th. That's a pretty big number. That now is compared, so Z sub C, if I convert, that's minus J, 1,592 K. Because Z sub R was 16K. I'm now combining 16 with 1,600. 1,600 dominates, doesn't it? That's my denominator. If I plug those numbers in up here, I now have minus 1,592 times 10 to the 3 over 16 times 10 to the 3 plus, well, this is now minus J 1592 times 10 to the 3 times 1 at 0 degrees. You can do that. Did I do that correctly? I don't want to forget my J's. Have to keep track of the J's. Now I have a minus J 1,600 over 16,000 minus 1,600,000 J. Do you see that the imaginary parts basically are the only things in that equation on the top and the bottom? You're basically taking a a complex number and dividing by that same complex number, what would you expect to get? 1. So this ratio is basically saying I'm not going to be changing my output voltage across that capacitor much in the sinusoidal steady state at 10 hertz. You can go through the exact analysis, but I'm going to say this is approximately 1 at 0 degrees. And what does that say V sub 0 of t is? That's now approximately 1 cosine 2 pi f t, because I had now, let's say, minus 0 degrees. Since my V sub 0 bar was approximately 1 at 0 degrees. This 1 is there and the 0 is there. Let's do the second case. Is that what I was calling it? Yeah. Let's do the second case. F is now equal to 1,000 hertz. Everything is the same except for omega. Now we have V sub 0 bar is the same formula What's changed is Z sub C. That's 1 over j omega c. This is now 1j. Omega is 2 pi times 1,000. C is the same. This now changes or can be simplified to minus j 15,915.5. And doesn't that look almost like 16,000? We had a 16,000 resistor. Now we have a real part about the same magnitude-wise as our imaginary part. Or when we now look at V sub 0 bar, we now have minus j 15,915 over 16,000 minus j 15,915 times 1 at 0 degrees. If we factor down a 16,000 from that, do you see what we would have? Let's do a 16,000. Let's just kind of play fast and loose here. We have a minus j up top. And downstairs we have a 1 minus j. You can go through this more accurately, but I'm just trying to quickly give you a feel for what to expect. Those now cancel. And what is minus j? Or here, let's just do it the old school way. Let's rationalize the denominator by multiplying by its conjugate. And we now have minus j minus j squared upstairs, and downstairs we have 1 plus j minus j squared. Or what do we now have? Minus j plus 1 over 1 plus 1 We now have 1/2 minus j 1/2, or that's 1/2 square root of 2 at an angle of minus 45 degrees. And now we know what our v sub 0 of t is at 1,000 hertz. It's now the square root of 2 over 2, or 0.707 cosine 2 pi 1,000 t minus 45 degrees. I've now worked most of your pre-lab. Now you need to do the last case, which is 100,000. But do you see now we're starting to attenuate the output waveform? At 10 hertz, we didn't attenuate it at all. Now we're down to 0.707. That's called the half power point. That's actually the cutoff frequency. Then at 100,000, we're going to have a much smaller magnitude for the output waveform. I'll let you do that by Saturday. I'll see you tomorrow, and we'll start with Chapter 9 more formally tomorrow.